Good evening, Lower Six. This week, we've just got a short little bit of a topic for you to have a look at in electricity, which is semiconductors and superconductivity. This isn't going to take us too long to do, so I'm going to set you some work and probably have it in by Wednesday, please, if that's possible. So I've got a couple of demonstrations here for you today of thermistors and LDRs. Now these are examples of semiconductor materials. We've already met one semiconductor because we had a look before at diodes, and these are two other types of semiconductor. A thermistor is, well, its name comes from thermal and resistor, which kind of explains really what it is. It is it's a type of resistor, if you like. It conducts electricity, but its resistance changes with temperature. Now this is what a thermistor looks like. I've got one in here. It's actually I've got it in a balloon just to protect it from the water. But if I hold it close to the camera, okay. So if the camera's focusing on that, maybe I'll put my hand behind. There we go. So it's actually quite a small thermistor. This, you can see that little sort of disc-shaped thing at the end there. That is a thermistor. So as I say, it's a type of semiconductor. Now semiconductors are not as good a conductor as a metal, such as copper, but they are obviously better than insulators. And one of the properties of semiconductors is that their conductivity can vary depending on what's happening outside. And in the case of thermistors, and you don't really need to know the details of how this works, the science behind how it works, but the number of charge carriers that are inside the component increases with temperature. So basically more electrons are being produced, which can then flow as charge carriers when the thermistor is at a high temperature. Now, an increased number of charge carriers means that its resistance drops. Okay, so its resistance changes in a very, very predictable way with temperature. So I'm going to demonstrate this now because I've got two beakers full of water at different temperatures. So we've got some ice water here, which is at pretty much 0 degrees, as you would expect. And here's some water which I've just got out of the kettle. It's cooled down a little bit, so it's 82 degrees, so it's pretty hot. Behind we've got a multimeter which can measure resistance. Now, of course, you could just use a voltmeter, an ammeter and a power supply to do it, and then use R equals V over I. But this is a bit more straightforward if you just use a multimeter, which I've set up to record in ohms resistance. So I'm going to take my thermistor and I'm just going to connect it to the multimeter, and you can see instantly that the resistance is 26.2. Now that's actually in kilo ohms, so it's 26.4 now, 26.4 thousand ohms. Now that's at presumably room temperature-ish. If I squeeze the end, it'll warm it up a bit, and you can see instantly as I'm squeezing the thermistor, the resistance is going down. Let's make it a bit more dramatic than that. Let's put it in these beakers of water. Now, this is an experiment, of course, we could have done in the lab if we'd been in school. So first of all, I'm going to put it in the ice water. So the temperature will drop, we hope, to close to 0, and you can see instantly the resistance is rocketing up. Okay, it'll probably go up to, once it settles, probably about 80 or 90,000 ohms. While it's just settling down, I'll show you what a graph would look like of resistance against temperature for a thermistor. So you can see that the shape of the graph, that at 0 degrees centigrade you've got a very high resistance, and then that drops in a normal sort of exponential-like curve as the temperature gets higher, and that's very predictable. So you can use thermistors in sensing circuits. You can use them in circuits where devices have to be switched on and off depending on the temperature, such as central heating systems or warning lights, or ovens, or air conditioning. So thermistors have quite a wide variety of uses. It is settling down there, isn't it? It's settling down at about 72. Okay. It's just taking a while for the thermistor to get into thermal equilibrium with the ice water. It's probably not going to go up too much higher than that. So that's at 0 degrees centigrade. Of course, if we're doing this experiment properly, we'd have a wide range of different temperatures, or maybe we would heat the ice on a Bunsen and then raise the temperature gradually and measure the resistance. But if I stick this into the hot water, well, you can see instantly what's happening there. Okay, temperature of hot water is now 75 degrees, and you can see that the resistance is dropping. So we're down to 5 kiloohms. Remember, it was 72 kiloohms before. 4.2, 4.1. If it carries on going down, we'll actually have to change the scale on the multimeter, but I don't think it'll go down too much lower than that. If I do change the scale, you can get an extra decimal point there, so 3.45 kiloohms. Okay, so that's the idea behind a thermistor then. So it's a resistor, if you like, that changes its resistance with temperature. Now, most thermistors, their resistance goes down with increasing temperature, and that's called a negative coefficient thermistor. You can sometimes get positive coefficient thermistors as well, where the temperature goes up with, the resistance goes up with temperature. But questions you'll be asked on in an A-level exam paper, it'll be almost entirely on negative coefficient thermistors, not positive coefficient thermistors. Okay, the most common type is a negative coefficient thermistor. You can almost think of a negative coefficient thermistor as being opposite to a light bulb, because if you think about a light bulb, as the light bulb gets hot, its resistance goes up. But with these things, as they get hot, their resistance drops, it goes down. Okay, so that is a thermistor. So I hope you understood that demo. There is another semiconductor device that I'm going to mention, which works in a kind of a similar way to a thermistor. And I've got one of them here. And I'll just hold that in front of the camera. Okay, you can see it's very tiny. Now, some people think they look like solar cells. It's not actually a solar cell, although it does react with light. This is a light-dependent resistor, okay, or an LDR for short. And the light-dependent resistor, again, it's another semiconductor device. It reduces its resistance if there is an increase in the number of photons of light falling on it per second. So an increased light intensity will decrease its resistance. Again, it's liberating electrons in the semiconductor and increasing the number of charge carriers that can flow around the circuit. Okay, and we'll demonstrate that now. I've got a torch somewhere, and I'll take the thermistor away and connect the multimeter to the LDR. Okay, so I'm assuming you can read the, let's put the LDR there. There we go. So I'm assuming you can read the multimeter there, and there's the LDR. So you can see the resistance of the LDR at the moment, about 10 kiloohms. So if it gets brighter, that resistance will drop. If it gets darker, that resistance will go up. So I'll show you darker by just putting my hand over the LDR, and there we go. So I don't have to put my hand very much over the LDR, and you can see the resistance has shot up to 65 kiloohms. In fact, I'll put it all the way on. It's going off the end of the scale. Okay. So very, very sensitive to the amount of light falling on it. Okay. Even moving my hand up here, out of the way of the camera, my hand's all the way up here, it's changing the resistance. So again, think about practical uses of an LDR. Well, you could have it on a security system. You can imagine a beam of light being fired at that LDR. And if that beam of light gets interrupted, it could trigger a burglar alarm. You could have an automatic light that comes on when it's dark. Okay. And there's some cars like Volvos have headlights that automatically come on, don't they, when it gets dark. So there's lots of uses for LDRs in circuits where you need to sense light. Okay. And I was going to show you what happens if I shine a light on it. So remember what you'd expect if the light level increases. You'd expect the resistance to drop. So here's a torch that I've got. So shine a torch on it, and you can see the resistance has dropped to 0.8 kiloohms. Okay, so there we go. So extremely sensitive. So those are the two components, thermistors and LDRs, you need to learn about this week. Now remember, if a thermistor or an LDR are kept in constant conditions, so constant light for an LDR, constant temperature for a thermistor, they would in fact just behave like normal resistors. Okay, so these two graphs I've drawn here for a thermistor. If you've got them at a constant temperature, they'll just behave like a normal resistor and obey Ohm's law. So a VI graph would be a straight line. Obviously, the gradient of that line would depend on the temperature, but as long as you're at a constant temperature, you would have a straight line relationship. So bear that in mind, that they do behave like normal resistors if the external conditions are kept constant. Okay. Now there is one other bit this week that I do need you guys to learn about, which I haven't got a demonstration of here, which is superconductivity. Superconductivity is a very sort of exciting area of modern physics. We only really sort of mention it in passing at A level. But superconductors are basically materials. In fact, a lot of materials do this. They're materials which, at a very low temperature, undergo a phase change. Okay, now you know about phase change is a bit like a liquid turning into a solid. Well, a lot of materials, particularly metals, at a very low temperature, they'll undergo a phase change whereby the atomic structure changes and electrons can pass through the material without dissipating any energy at all. So the electrons can pass through the atomic lattice in the material without dissipating any energy. In other words, their resistance or their resistivity drops to zero at a certain temperature. Now this temperature is sometimes called the threshold temperature or critical temperature. It's normally, for most metals, very, very, very low. So we're talking about a couple of degrees above absolute zero. And that makes superconductors not particularly practical for the uses which we could envisage for them if they're made out of sort of normal metals. Now think about uses of superconductors. Well, if you've got a conductor that doesn't dissipate any energy, that has zero resistance, you can have an enormous current flowing through it. So if you wanted to make some really powerful electromagnets, perhaps to float a maglev train, or to bend particles in a particle accelerator like they do at CERN, or medical applications where you have very powerful magnets, well, superconductors would be really, really useful for that. Okay. So superconductivity, very, very good for making powerful electromagnets. Also think about if you're distributing electricity and you don't want to lose a lot of energy, so you could have savings on the losses due to heating loss if you've got superconducting cables. But the problem is, of course, cooling something to nearly absolute zero, very, very difficult. So there is a lot of research going on at the moment into materials that superconduct at higher temperatures. And I believe there are some sort of very exotic metal oxides that they found which superconduct at temperatures of about 100 degrees above absolute zero. So about minus 170, that sort of degree centigrade, that sort of temperature. Now that's still pretty cold, but that does make it more practical. That brings it into the range of things like liquid nitrogen could cool something down to that temperature, which is readily available. Of course, what would be really cool is if we could have materials that superconduct at room temperature. If that happens, the number of applications for that would be astonishing. We'd be laughing really. But anyway, that's superconductivity. Very interesting topic. We only really sort of mention it, and you might be asked to define what the threshold temperature is, and explain some of the possible uses of superconductivity. Don't really have to go into the physics. Physics is very interesting. It sort of touches onto quantum mechanics and some very exciting areas of physics, but it's a bit beyond the level of A level. Okay, so that's it. I will set you a bit of work to do for Wednesday this week, and of course we'll see you again. I know we didn't see you on Thursday for a Zoom lesson, but we'll see you for a Zoom lesson this Thursday. Okay, thank you guys.